Yo, all right. AP tests are over. Learning continues, though. All right, so take a look what we got on the screen here. Right, we're taking the derivative of a product, f of x times g of x. Derivative of product, you have to use the product rule. We have first times the derivative of the second plus the second times the derivative of the first. Why am I showing that to you, right? We already learned this. Well, I want to show it to you for this reason. We're going to develop or derive a new integration technique, and it's going to come from the fact that every differentiation formula has a corresponding integration formula. So maybe let me take like a little aside here for a second. What if I said, hey, what's the derivative with respect to x of x squared? I think you guys would have no problem saying that's just going to be 2x to the 1 or just 2x, right? That's a differentiation formula right there. Well, that means there is a corresponding integration formula, because if the derivative of x squared is 2x, right, we sometimes think of that as going forward. Well, then why can't I just go backward? And I'm putting backward in quotes, by the way, right? And you can, right? So in other words, the integral of 2x dx, what would that be? Well, the way I would do this, find the antiderivative. Do I know a function whose derivative is 2x? And the answer, of course, is yeah, you do. It's x squared. So we go backwards. There's a little caveat here, right? Because it's a little bit more than that, because when you're going backwards, right, what do we have to kind of add? We have to add that constant of integration, because x squared plus x, that is a family of functions differing by a constant whose derivative is 2x. And obviously that is because the derivative of a constant is 0. All right, but the idea is that if I start with if I start with a differentiation formula or a derivative formula, I can then write a corresponding integration formula. So let me kind of take this and slide this a little bit out of the way here, right? And just use it as reference, right? Here's a differentiation formula. Well, hey, look at this. We have a differentiation formula right here. So that means I should be able to write some sort of corresponding integration formula, and I can, right? So kind of look at what we did here, and then we can apply that same thing here. So we basically can say that the integral of the right side, which, by the way, the integral of the sum is the sum of the integrals. So I can write this as the integral of f of x times g prime of x dx plus the integral of g of x times f prime of x dx. That's just me taking the integral of the right side, but I decided to apply the rule that the integral of the sum is the sum of the integrals. That's why you see two separate. That's going to equal this right here, right? Just like the integral of 2x equaled x squared. Well, the integral of all of this stuff is going to equal that stuff. But again, we have to do exactly what we did before, which is we have to kind of include that constant of integration right there, okay? Which technically we'll talk about what we can do with that in a second. Anyway, so that's what we get. So we start off with that. So we're real excited about that. All right. So now that we have that, I'm going to kind of get rid of this, and I'm going to manipulate this equation down here. So if I wanted to, I can go ahead and solve for maybe this guy right here. So in other words, if I was going to solve for this integral, right? It's, you learn this in secondary math, right? Mrs. Trifoletti probably taught you this. If you're solving for this, you need to isolate it. So you're going to get rid of this. So plus integral, to get rid of it, I'm just going to subtract it. So I'm going to subtract that integral from both sides. So I'm going to write, okay, let's see here. I have f of x times g of x, because that's on this side of the equal sign. I'm now going to subtract this integral here, which is going to be g of x times f prime of x, right? And then that's going to equal the integral of f of x times g prime of x dx. Now, kind of a little wacky, because you're like, well, what'd you do with the plus k? Well, k is a constant. And if you think about it, when I do this indefinite integral here, I'm going to add a constant there. So I don't really need to have this, because there's going to be one created from this. All right. So that's why I kind of magically got rid of that. All right. So now here's the next thing. All right, just to clean this up, you might be saying, why do you want to do this? First thing I'm going to do is I'm going to swap this around. All right, we like to read left to right, right? So I'm going to say, all right, let me start with this. The integral of f of x times g prime of x dx. It turns out that if we have that, if we see an an integrand that fits this form, we know that that's equal to f of x times g of x minus the integral of g of x times f prime of x dx, right? And we basically just derived that from the product rule for the derivative. All right, so what's the point of this? Well, this is the point. If you come up to an integral problem, you might get this integrand, and this might be a mess, all right? So might be, I can say a mess or might be tricky to do. In other words, you can't look at this and say, hey, I recognize a function whose derivative is that, or apply some basic rule that or do a use substitution that's going to work. Like, this might be a mess. But if you write this in its equivalent form, right, you still get an integral in it. But here's the deal. This integral may be nicer. So this may be nicer, right? We're using fancy math words here, nicer. And nicer basically means if it's the equivalent or easier difficulty, that usually ends up being a really good thing. And yes, I said equivalent, and that might seem wacky to you. And when we get to that problem, we'll do it. But yes, so if it's the same or better, that's good. So now a couple things. This is pretty kind of abstract, right? So you're like, what are you talking about? So let's clean this up with some common variables that are used in its place. So let's go ahead, and this is going to be the process. You're going to look at an integrand, and you're going to have to decide on two things. You're going to have to pick a u. So let me switch the color up here. You're going to have to pick a u, and you're going to have to pick a dv. Not du, a dv. You have to pick them. And you have to pick these things in such a manner that you pick everything. Everything has to be accounted for. So I'm going to pick my u here to be f of x. I'm going to pick my dv to be the rest. So it's very different than our normal use substitution stuff that we've done. Okay. Now, why did I do this? Well, I have to do this because I have to account for everything. So now I did, right? F of x, that's just my u right here. And g prime of x, that's just my dv. So all of that was accounted for. Now, once I do that, once I pick my u and my dv, I'm going to compute what du would be, and I'm going to compute what v would be. Well, if I have u and I want to compute du, that's just going to be the derivative of u. And then, of course, I have to do dx there to get the differential. Okay. What do you think I have to do to go from dv to v, right? We haven't had to do that. We're going from dv to v, right? That seems a little weird. And hopefully you're saying you're going to have to integrate, right? So now I have to integrate. So to get v, I have to think of, right, do I know a function whose derivative is going to be g prime? The answer is you do. It's going to be g of x, okay? You can see the du has the dx, the dv has the dx. So now why? What was the point of that? Well, again, the point was take a look at what we got here. F of x in our little substitution technique here is u, okay? G of x, turns out that's v. G of x, v. F prime of x dx, that's du. So a lot of times, instead of using f's and g's and of x's and primes of x's, what you'll see in a calculus textbook, in most calculus textbooks, is that if you have the integral of u dv, it's equal to uv minus the integral of v du. All right. And that, my friends, is the formula for integration. Oh, that was a delay on my writing. That's why I didn't spell it right. All right. Let me try that again. I want to spell that right. I got a little slow up there. All right. So I'm not a good speller, but I got to be able to spell integration if I'm a math teacher, right? So integration, still working bananas, by parts. All right. That's what this is. Integration by parts formula. It's something that I just derived it for you because honestly, I wouldn't be able to go to sleep at night if I just showed you this formula. It didn't tell you where it came from, but at the end of the day, you just have to know it, memorize it, and then use it. What is it? It's basically another tool in your little toolbox to solve integrals. So when all else fails, when you exhaust everything else that you've learned to this point, all right, you're going to try this technique of integration by parts. And you'd make me real proud if you understood that it actually came from the formula, differentiation formula for the derivative of a product. All right. So that is the derivation of integration by parts. All right. So let's just do one problem and be done with it. All right. So here we go. You ready? Problem one. You have the integral of x e to the x dx. All right. So I want to integrate that. So you're like, all right, what can I do? Back in the day, maybe you would try a u substitution, right? But that's not going to work here, right? Like if typically with the exponentials, we have been letting u equal that exponent. But if you let u equal x, du is just dx, and this x is not getting accounted for, right? If this would have been e to the x squared, then a u sub would have worked because you could let u equal x squared, and then du would be 2x dx, and the world would be great, right? Everything would align. All right, but that's not what it is. This is what it is. So u sub, not going to work. If you don't believe me, try it and then watch the dead end that you go into. So then you're like, all right, well, do I recognize this? Do I know a function whose derivative is this? No. Can I simplify it? No. So, all right, lucky for us, we learned this new integration by parts formula, which a lot of times is very useful when you have products. Because remember, there is no product rule for integration. Okay, so what do you have to do? The big thing is you have to pick a u and a dv. You got to make sure that you pick a u and a dv so that it accounts for everything. And there is a method to what you pick. All right, you can pick wrong, and I'll give you an example of what happens when you do that. I'm going to hook you up on this one. I'm going to say, you know what? Let's let u equal x. And you're like, back in the day, you told us never to let u equal x. Well, this isn't a standard u substitution. This is integration by parts. So u is going to be x. dv now has to be the rest. So pause the video. What's the rest? Hopefully you said it's e to the x dx, right? So think about what you did here now. This is u and this is dv. That's the ultimate goal, all right? To express the integral as the integral of u dv. That's the ultimate goal if you want to use parts. So now once you pick your u and your dv, you then figure out du and v. Well, du is the derivative of u, which would be 1, and then times dx. V is the integral. Well, it looks like I'm not doing anything here, but I am, right? Do I know a function whose derivative is e to the x? Easiest one in America. It's e to the x. So now I have everything picked. So again, think about it. I have the integral now expressed as the integral of u dv. Well, based off our cool little derivation, we know that this is equal to uv minus the integral of v du. That's what it's equal to. So now if I apply that, I'm going to get that this integral here is equal to u times v. So u is x, v is e to the x. So that's going to be x e to the x, that's my u times v, minus the integral of v du. So that's going to be e to the x dx. And hopefully you're like, oh, check it out. All right, I get it. This I had no idea what to do with. I apply this little integration by parts technique, and now this integral is nicer. Looks pretty, whatever you want to call it, right? Why? Because you can do it. You know a function whose derivative is e to the x. It's just e to the x. And now since it's an indefinite integral, I just put in that constant of integration there, and I end up getting x e to the x minus e to the x plus c. So there is my answer. This is a family of functions differing by a constant, such that if I was to take the derivative of this, I would get something that simplifies to x e to the x. That is integration by parts. Now, let's pick wrong, and then we'll be done. So what if you pick wrong? Okay, what does that mean, pick wrong? Well, maybe you got this problem, and you're like, all right, I opted to let u equal e to the x, and then dv equal x dx, right? So the dv has to have the dx. That you can't really debate. The dv has to have the dx, but you get to pick the rest of it. So now, again, you have to understand that I'm picking everything. All right, multiplication is commutative. I can multiply in any order I want here, right? So here is my u part, and then the rest is picked, right? The rest is x dx. That's my dv part. So I was able to capture everything. That's very important. So now let's go through it. Let's compute du, which the derivative of e to the x is just e to the x. So du would be e to the x dx. V, do I know a function whose derivative is x? I do. Remember, I'm going backwards now. If you said 1, you're thinking the wrong thing. I'm going backwards to get v, right? From dv to v, I have to integrate. So that'd be 1 half x squared. You might also be saying, and I didn't mention it here, why don't you do plus c? Again, that comes into play with this integral, so that's why I don't need to do it. And so now watch what we get. I'm not going to rewrite this because this is the formula. I express this integral as u dv. So that means it should be equal to u times v, which is going to be e to the x times a half x squared. I'm going to switch the order of multiplication there and make it look prettier. 1 half x squared e to the x. So that's u times v minus the integral of v du. So, all right, that's a half x squared times e to the x. If I wanted to be cool, I can pull the half out because that's a constant, but I still have that x squared e to the x dx, right? So now take a look at that. The whole point of doing integration by parts is so that that integral in the formula is nicer, all right? This is x squared. I kind of made it worse, right? Because u sub's still not going to work here. Okay, so this got worse. This got worse. All right, so that's no bueno. So that means, hey, what do? Back to the drawing board. Pick something different. And obviously the thing to pick here was letting u equal x in this particular problem. So this is a good non-example of what not to do. Now, you're like, how am I going to know what to pick? Here's the deal. You just got to practice. You got to do different problems. All right. You got to recognize patterns and forms, right? Right now we have a polynomial times an exponential. When you have that specific type of product, polynomial times exponential, and all else fails, then you would think, all right, I'm going to let u equal the polynomial and I'm going to let dv equal the exponential. And more times than not, that will lead you to the promised land. That will not always be the case. Depending on the structure of the integrand will depend on what you pick. And so what we will have to do over the next, 10 days basically is to give you different types of structures or integrands, and then for you to decide, all right, how am I going to pick my u and my dv so that I can evaluate this indefinite integral? Okay? All right, so that's that. There is nothing for you to submit today. Tomorrow at 10 o'clock, we will get on and we will basically do a similar problem and a couple other problems that you can do with me, and then submit them right there. And then you don't have to worry about it. Okay? Hope all is good. Stay safe. Take care.